Hello everyone, welcome to the online lecture series of the course EE204 Digital Electronics and Logic Design, Module 4 Sequential Circuits and Asynchronous Counters. Today we are going to study about asynchronous counters. A digital counter is a set of flip-flops whose states change in response to pulses applied at the input to the counter. The flip-flops are interconnected so that their combined state at any time is the binary equivalent of the total number of pulses that have occurred up to that time. Thus, a counter is used to count pulses. A counter can also be used as a frequency divider to obtain waveforms with frequencies that are specific fractions of the clock frequency. They are also used to perform the timing function as in digital watches, to create time delays, to produce non-sequential binary counts, to generate pulse trains, and to act as frequency counters, etc. Counters may be asynchronous counters or synchronous counters. Asynchronous counters are also called as ripple counters. Ripple counter is the simplest type of counter and it is easy to design and requires least amount of hardware. In ripple counter, flip-flops within the counter are not made to change the states at exactly the same time. This is because the flip-flops are not triggered simultaneously. Ripple counters are also called as serial or series counters. Synchronous counters are clocked such that each flip-flop in the counter is triggered at the same time, and the synchronous counters are faster than a synchronous counter. Each of the counts of the counter is called the state of the counter, the number of states through which the counter passes before returning to the starting state is called the modulus of the counter. Hence, modulus of a counter is equal to the total number of distinct states or counts, including zero, that a counter can store. Or, in other words, the number of input pulses that causes the counter to reset to its initial state is called the modulus of the counter. A counter may be an up counter or a down counter. An up counter is a counter which counts in the upward or ascending order, and a down counter is a counter which counts in the downward or in the descending order. Let us discuss these asynchronous counters in detail. Consider the example of a 2-bit asynchronous up count. The 2-bit asynchronous up counter counts in the order 0, 1, 2, 3, etc. or in binary form 0, 0, 0, 1, 1, 0, 1, 1, etc. Which means after every 4 clock pulse, the counter will reset to its initial state and it will continue the counting operation. Usually, T flip-flop are used for asynchronous counters. Since we are using JK flip-flop must be operated in toggle mode, which means the J and K input must be connected to a logic high. Here, the first flip-flop is provided with the clock signal and the second flip-flop is having a derived clock from the output of first flip-flop. That is, the output of first flip-flop Q is connected to the clock of the second flip-flop. The output of the flip-flop, which is provided with the clock signal directly, is the LSB of the binary pattern, and the output of farthest flip-flop from the flip-flop which is provided with the clock signal act as the MSB. From the timing diagram, you can clearly verify the working of the 2-bit asynchronous up counter. For the first clock pulse, initially both the flip-flops are in reset condition. During the first clock pulse, the first flip-flop output toggles and becomes 1. At this time, the clock is obtaining a 0 to 1 transition. Since we are using a negative edge triggered flip-flop, this will not change the output of the second flip-flop. Hence, second flip-flop output will remain as 0 itself. During the second clock pulse, the first flip-flop output toggles and it will become 0. At this time, there is a 1 to 0 transition at the clock of the second flip-flop, which will trigger the second flip-flop and thus its output will become 1. So at the end of second clock pulse, the output will become 0, 1. During the third clock pulse, the first flip-flop again toggles its state and it will become 1, whereas the clock signal available at the second flip-flop will not trigger the second flip-flop and hence its output will remain same as the previous output, that is 1. During the fourth clock pulse, again flip-flop output 1 will be toggled to 0, and at this time there is a 1 to 0 transition at the clock of the second flip-flop and it will change the output of the second flip-flop, which makes it to 0. So at the end of fourth clock pulse, you can see that both the flip-flops are having the same initial state 0, 0. And this pattern will continue during the next clock pulses also. To have a clear idea of the working of a 2-bit asynchronous up counter, let's have a live simulation. Here you can see a similar circuit as shown in the previous slide. So before starting the operation of 2-bit asynchronous up counter, let's check the output of the flip-flops independently using the asynchronous inputs. So making the preset input to 0 will set the flip-flop and making the clear input to 0 will reset the flip-flop. So now let's start the upcounting operation. Initially the flip-flop outputs are in the reset, that is 0, 0. So after giving the first clock pulse, the flip-flop output changes to 0, 1. Now apply the second clock pulse. Applying the second clock pulse, the flip-flop output will changes to 1, 0. The first flip-flop toggles its state to 0 and second flip-flop toggles its state to 1. The second flip-flop will receive a clock signal for every 2 clock pulses received for the first flip-flop. So for the next clock pulse, the flip-flop output will change to 1, 1. Now providing the next clock pulse, both the flip-flop will toggles its state and reset the counter to 0, 0. From the simulation, it is clear that the second flip-flop will change its state for every 2 clock pulses received for the first flip-flop. If you increase the number of flip-flops, you can generalize this statement for every nth flip-flop in the counter circuit. The flip-flop output will change for double the number of clock pulses received for its preceding flip-flop. Now consider the case of a 2-bit asynchronous down counter. A 2-bit asynchronous down counter counts in the order 0, 3, 2, 1, etc. or in the binary form 0, 0, 1, 1, 1, 0, 0, 1, and it repeats. The circuit diagram is similar to that of a 2-bit asynchronous up counter. The only difference is that here the clock input for the second flip-flop is provided from the Q bar output of the first flip-flop. Instead of Q output, here Q bar output is connected to the second flip-flop. Here also the first flip-flop will act as the LSB, which is provided with the direct clock signal, and the second flip-flop, which is receiving the indirect or derived clock signal, act as the MSB of this binary pattern out. So in order to have a thorough understanding, let's have a live simulation. So consider a 2-bit asynchronous down counter circuit as shown in the previous slide. Here you can observe the only difference from the up counter circuit is that the second flip-flop is receiving the derived clock from the complemented output of the first flip-flop. So checking the flip-flop output using the asynchronous input, changing the preset to 0 will set the flip-flop output, and making the clear input to 0 will reset the flip-flop. Now to start with the counting operation, initially the flip-flop is in reset state. So at the end of first clock pulse, both the flip-flop has toggled its state. As the first flip-flop is in toggle state, it will change the state from 0 to 1. Since initially Q bar is having a 1 and now the Q bar is changed to 0, this will act as a clock signal for the second flip-flop, which will make the second flip-flop also to toggle its state from 0 to 1. Providing the next clock pulse, the first flip-flop resets to 0, whereas the second flip-flop will continue its state. That is, now the output is 1 0. Upon giving the next clock pulse, the first flip-flop again toggles its state from 0 to 1, and at this time the second flip-flop will receive a clock signal and it will toggle its state from 1 to 0, which makes the output to 0 1. On giving the next clock pulse, the first flip-flop toggles its state to 0, whereas the second flip-flop will retains its state as 0 itself. Now the flip-flop output has resetted to its initial state 0 0. I hope with this explanation you are familiarized with the working of a 2-bit asynchronous up counter and a 2-bit synchronous down counter.